What if I told you that a completely ordinary-looking crystal, something you could hold right in the palm of your hand, is hiding one of the strangest and most fragile secrets in physics? We're talking about quantum entanglement. When particles become entangled, they share a single deeply connected state, perfectly syncing their properties no matter how far apart they are. Albert Einstein famously struggled with this idea, dismissing it as spooky action at a distance. For decades, the consensus in quantum mechanics has been that this spooky connection is incredibly delicate. The moment entangled particles bump into the chaotic outside world, the connection shatters. That is why physicists normally lock these experiments away in highly controlled environments, like the deep freeze of a dilution refrigerator. But a recent experiment revealed that these connections can survive in much larger systems. Researchers discovered evidence of quantum entanglement existing inside a centimeter-sized chunk of a material called Ce₃Pd₂₀Si₆. It is a strange metal, and it is massive compared to the tiny, isolated atoms we usually study. Finding this behavior inside a visible object raises a new question. What is it about the structure of a strange metal that allows these fragile states to persist where they should otherwise be destroyed? You can't exactly stick a rock under a standard microscope and see quantum entanglement. To prove it was there, the research team traveled to the city of Grenoble, France. They set up their experiment at a specialized particle facility called the Institut Langevin, hoping to look inside the crystal without destroying the fragile states within it. Their tool of choice for this delicate operation is a technique known as inelastic neutron scattering. Think of this like standing at the mouth of a pitch-black cave with a handful of pebbles. You can't see the walls, but if you throw the pebbles into the dark and listen to exactly how they bounce and echo back, you can determine the unseen shape of the cave. This animation shows the process at the atomic level. Instead of pebbles, the scientists fired a continuous beam of neutrons directly into the strange metal crystal. By measuring the exact angles and speeds of the neutrons bouncing off the internal atoms, the team could track how those atoms were vibrating together. The scattering data provided the echoes, but proving those vibrations were the result of entanglement required a specific mathematical framework to analyze the movement. The researchers used a tool called quantum Fisher information, or QFI, to process the data. QFI measures responses to disturbances. On the left, particles react randomly. On the right, a synchronized cluster responds as a single connected team. Using QFI calculations, researchers found atoms inside the crystal acting in unison. Groups of at least 9 constituents were entangled. While these results are significant, it is important to clarify the actual scale of the discovery compared to some of the more sensational reports. The researchers did not turn the entire crystal into a giant version of Schrödinger's cat. The crystal itself was not in a state of quantum superposition that you could see with the naked eye. Detecting these 9 particle clusters still required an extreme environment. The crystal had to be chilled to 60 millikelvin, just a fraction of a degree above absolute zero, while held inside a precisely tuned magnetic field. The experiment demonstrates that while the entire crystal isn't a single quantum object, its internal structure facilitates microscopic clusters that act in unison, even within a macroscopic piece of matter. Why does finding entanglement inside this specific metal matter to the broader physics community? It links back to the mystery of strange metals. For decades, physicists couldn't explain why these materials behave so differently from regular metals. This experiment suggests that hidden networks of quantum entanglement are the mechanism driving their unusual electrical properties. Isolating these quantum states provides the foundational knowledge needed to eventually build more sensitive quantum sensors or to better explain the mechanics of unconventional superconductors. This discovery bridges a gap between the isolated quantum world and the materials we interact with every day. It shows that quantum effects are active and measurable even within a solid, visible object. As our measuring tools improve, we may find that these hidden quantum worlds are much more common than we once thought. Do you think quantum mechanics will eventually transform everyday technology, or will it remain a phenomenon of the lab? Let us know in the comments and subscribe for more deep dives into the universe.